Hi, today we'll see about contour integration of the type integral x sin mx by q of x dx or integral cos mx by q of x dx. So we'll start with the problem. Evaluate integral 0 to infinity x sin x by x square plus a square dx using contour integration. So when a problem is given in this way, and you can clearly see here x sin x in the numerator and x square plus a square in the denominator. So you just want to convert this into a contour. You can see this picture. There is a contour. So this contour is having a real line. Okay. So it goes like from minus into plus empty, but we restrict with minus r to plus r. So it starts from minus r to plus r and just passes through a curve in anti-clockwise direction. So that is C1. So altogether this is your contour C. So we consider here the integral C. Here you have x sin x, right? So you rewrite it as z into sin x. We are writing it as e power I z instead of sin x. Okay, so you write z into e power I z by z square plus a square dz. So just consider like this. Now using contour integration, we can say integral over c z e power I z by z square plus a square dz equal to integral minus r. So we just have this contours because this contour is having two parts. One is minus r to plus r, the other one is c1. So integral minus r to plus r x e power ix by x square plus a square dx plus integral over c1 z e power iz by z square plus a square. Let us name it as equation 1. Now we need to find this integral over c z e power iz by z square plus a square dz, right? So consider this. Now we can take this inside integral, what is there, that is your f of z, that is z e power iz by z square plus a square. Now we need to find the poles of f of z. What are the poles of f of z? You equate the denominator to 0. So z square plus a square equal to 0 implies z square equal to minus a square, that is z equal to plus or minus root of minus a square, which is plus or minus ie. So you have two poles, one is minus ie, the other one is plus ie, and their power is 1. That means these poles are simple poles. That means the order of the pole is 1, right? So clearly in this contour C, the pole is equal to minus IA lie outside C, and the pole is equal to IA lies inside C. So how is that? We'll see that. You can see here. So this is your imaginary part, and this is your like real part. So in this we have z equal to minus ia and z equal to plus ia. So z equal to plus ia in the sense you have somewhere like e, because that is in the imaginary axis. So this is clearly inside the contour. When you talk about z equal to minus ia, which is minus a here, this place, so this is outside. That means here z equal to minus a is outside, z equal to ia is inside. So clearly we can see the pole z equal to ia is lying inside this contour, and the pole z equal to minus I is lying outside the contour. So that is what we mean here. Now let us find for this, one second. So for this z equal to plus ia, we will find the residue. So to find the residue of the simple pole z equal to ia, so we know residue formula, residue of z equal to f of z equal to limit z tends to a z minus a into f of z. But here we have the poles z equal to ia. So residue of z equal to ia, f of z equal to limit z tends to ia, z minus ia into f of z is z e power iz by z square plus a square, which we took. Now again we follow the same step here, but when we have this z minus ia, we need to expand this z square plus a square. So z square plus a square is z plus ia into z minus ia. So cancel this z minus ia, z minus ia. So that will leave out this z equal to, sorry, z into e power iz by z plus ia. So I hope you are clear with this. Then finally we need to substitute this ia in place of z. So ia into e power I into ia by ia plus ia, which has been written here. But what is I into I? I into I is I square, and you know I square is minus 1. So we replace I square is minus 1 into e, which is e power minus e. And still you have ia here, but in the denominator you have ia plus ie, which is 2ie. Now we can cancel this ia and ie, leaving out e power minus e by 2. So I hope you are clear with this step. Now this is the residue of z equal to ie f of z, but we need to use Cauchy residue theorem. You can see by Cauchy residue theorem, integral over c f of z is equal to 2 pi into sum of the residues at its poles. So we have only one pole z equal to ie. So we have f of z is this one. Okay, integral c z e power I z by z square plus a square dz, which is 2 pi into e power minus a by 2, and cancel this 2 and 2, leaving out pi a into e power pi I into e power minus e. So now we got this result. So this one we need to replace here, where in equation number 1, which we took before. Okay, this is equation number 1. In this equation, this place we need to substitute that result. But what about this side? The entire side we need to go with some working. Okay, we'll do that. Right. So here you can see. So this place I substituted pi I into e power minus e in equation 1, but in the right hand side it is still the same. Now we need to take limit r tends to infinity on both sides. We have wherever we have this terms, we just take limit r tends to infinity. So here and here and here, all these places we take limit r tends to infinity. Now why should we do this? Because we need to get the result with respect to the contour. You can see clearly this part, when r tends to infinity, this integral over the curve C1 z e power I z by z square plus a square becomes vanished. That means it becomes 0 by a theorem called Jordan's theorem. So this will go. So how is it? You can see here. So by Jordan's lemma, this term is getting nullified. That is, this term is vanished. This term is 0. So when you substitute that as 0, you will be seeing only these terms which has been written here. Okay, right. Now what is this integral minus into plus infinity? This one. Okay, this quantity, this integral, we got pi I into e power minus e, but we need integral 0 to infinity, not minus into plus infinity. So how should we do that part? So here, this one again, e power ix can be written as cos x plus I sin x, which you know very well, right? So you just multiply that inside. So you have cos x plus I is sin x. So multiply this. You have x into cos x plus I into x sin x. That I have done here. You can see. And remaining terms and all are same. So we have all these steps. And now you split this integral. Integral minus into plus infinity x sin x by x square plus a square plus integral ix by x square plus a square. Pulling out I, so you had only x sin x by x square plus a square, right? The other side is pi I into e power minus a. Now we equate the imaginary part on both the sides. You get imaginary part is leaving out this I. Without I, we will write the other terms. Okay, all this terms. So we have integral minus into plus infinity x sin x by x square plus a square dx equal to pi into e power minus a. That means you won't get this I, except that we get this term. And real part, of course, you don't have anything, so it's going to be 0. So we have only imaginary part here. Now still we need 0 here. So what should we do? You can see here we have the property. If you take this term as f of x, now you replace this, all this places x by minus x. So we'll be replacing here x is minus x. So f of minus x is minus x sine of minus x whole square plus a square, and sine of minus x is minus sine x. So we have minus x into minus sine x is x sine x, and minus x whole square is x square plus a square. So you have x sine x by x square plus a square, which is equal to f of x. So we have f of minus x as f of x. That means that f of x is an even function. So whenever you have negative values substituted in that variable, you get the same, the same variable back. That means when you substitute negative and you get the same function, then it is going to be an even function, right? Now, when it's going to be an even function, then this we have the property of integral minus into plus infinity f of x dx is 2 times integral 0 to infinity f of x dx if f of x is even. So using this property, we could convert this integral minus into plus infinity x sin x by x squared plus a squared dx is 2 times integral 0 to infinity. So that is what I have done here. This one has been converted as 2 times 0 to infinity, which is pi e power minus a. Now we need this result, right? Integral 0 to infinity x sin x by x squared plus a squared dx is pi e power minus a by 2. Okay, so that is the final answer. So finally we obtain this result. So that is how the problem goes on. I hope you understood this problem. Thank you.